Okay, now in the previous video we defined the divergence theorem. So basically it states that flux of a vector field out of a closed surface equals the integral of the divergence of that vector field over the enclosed volume by the surface. Let's consider the first example from the divergence theorem. So now we have a solid E bounded by two surfaces. The first surface is the xy plane and the second one is the paraboloid c equals to 4 minus x squared minus y squared. And so S is the boundary of E oriented with the outward pointing normal vector field. Now if our vector field F equals to this, we want to find the flux integral over the closed surface. So if I draw a picture, so we have this x, y and z axis. Then we have the paraboloid 4 minus x squared minus y squared. The paraboloid open downwards. You may see a paraboloid like this. And this is a closed surface because this paraboloid is bounded below by the xy plane. This is the closed paraboloid. So this one is c equals to 4 minus x squared minus y squared. The bottom surface is c equals to 0. Now as you can see, we have a closed surface. Therefore, to evaluate this flux integral, what we could do is we could use the divergence theorem. Otherwise, you have to consider the flux through the surface of the paraboloid and the flux through this part, which is a part of the xy plane. Okay, so let's use the divergence theorem. Okay, so from the divergence theorem, we get the flux integral over the closed surface S equals to the volume integral of the divergence of F over the domain bounded by these two surfaces. So let's say your domain bounded by these two surfaces is E. So that's your E. Okay. So let's calculate the divergence of F. Our vector field F is this one. This is your vector field. So now recall, if you have a vector field with three components P, Q, R, then divergence of F equals to scalar number. This is grad dot F. This equals to partial over partial x of P plus partial over partial y of Q. Q is the second component of the vector field, plus partial over partial C of R. Okay, so in this problem, this is our P, this is our Q, and this is our R. Therefore, the divergence of F equals to partial over partial x of xc times sine yc plus x cubed plus partial over partial y of cosine yc plus partial over partial c of this third component of the vector field, which equals to 3 times cy squared minus e to the x squared plus y squared. And so let's take the derivative of the first component with respect to the x variable. Therefore, we have to treat the variables y and c as if they are constants. So then you will get c times sine yc plus 3x squared. Okay. And then the derivative of the second component with respect to the y variable should be, derivative of cosine should be minus sine y times y of c, sorry, y times c times, now derivative of this inside part with respect to the y variable will give you the constant c plus 3y squared. Again, here we have to treat variables x and y as if they are constants. So derivative of this one, the first term with respect to the c variable give you 3y squared, and derivative of this second term with respect to the c variable is 0. Now, so we have positive c sine yc term here and negative c sine yc term here. We can cancel those two terms, and we have the divergence of f equals to 3x squared plus 3y squared. Great. Okay, so now we can do this triple integral. So therefore, the flux integral over the closed surface f equals to triple integral of 3x squared plus 3y squared over the solid domain E. Now, this is your solid domain. Now, to evaluate this triple integral, we could use cylindrical coordinate system, and the reason is, so here I see a term with 3x squared plus 3y squared, and if you factor out 3 you will get x squared plus y squared, and in cylindrical coordinate system x squared plus y squared equals to r squared. So if we use cylindrical coordinate system, we want the equation of this paraboloid in terms of r and theta. This is nothing but c equals to 4 minus r squared. So now the right hand side of the triple integral becomes, so 3 times x squared plus y squared dv solid domain E, and this equals to, so let's use cylindrical coordinate system, then our triple integral becomes 3 times r squared. Now in cylindrical coordinate system, our volume element dv equals to r dc dr d theta. Now the inner integral corresponds to the c variable. So let me consider a volume element like this. That's your volume element dv. Then the lower limit of c is 0. Upper limit of c is given by the surface of the paraboloid, which is 4 minus r squared. And then we need to consider the projection of this paraboloid on the xy plane. Now on the xy plane, if you look from the top, you will see a circle with radius 2. And the reason is this: so when this paraboloid intersect with the xy plane, your c coordinate becomes 0. So you have 0 equals to 4 minus x squared minus y squared, which is the same as x squared plus y squared equals to 4. This is a circle with radius 2. It means your r value goes from 0 to 2 and theta goes from 0 to 2 pi. Let me draw the domain on the xy plane. So, let's do this. So that's the circle x squared plus y squared equals to 4. Sorry. R goes from 0 to 2 and theta goes from 0 to 2 pi. Okay. Let's simplify the integrand. Your integrand becomes 3r cubed dc dr d theta. Now our first variable of integration is c. So we can treat 3r cube as a constant, and if you integrate 3r cube, you will get 3r cube times the variable of integration, which is c. R cube times c. Now the lower limit of c is 0, upper limit is 4 minus r squared. Apply the upper limit first and then minus the lower limit. So you will get 4 minus r squared minus 0 dr d theta. Great. Now let's distribute this 3r cube term. If you do that, you will get 12r cubed minus 3r to the power 5 dr d theta. Now let's integrate this term with respect to the r variable, and you will get 12r to the power 4 over 4 minus 3r to the power 6 over 6, and r goes from 0 to 2. Therefore lower limit should be 0 and the upper limit should be 2. If you apply the upper limit first, you will get 12 over 4 12 over 4 is 3. So you have 3 times 2 to the power 4 minus 3 over 6 is 1 half. 1 half times 2 to the power 6. And if you apply the lower limit, you will get 0 and 0. And so this is 2 to the power 5. And 2 to the power 4 is 16. 16 times 3 is 48. 48 minus, so basically your integrand is 48 minus 2 to the power 5, which is 32 theta. Finally, if you integrate this one with respect to the theta variable, you will get 48 minus 32 is 16 theta, and after applying the limits, you will get 16 times 2 pi minus 0, which equals to 32 pi. Now this is the way we used the divergence theorem to evaluate a flux integral over a closed surface. Now if you directly calculate the flux integral using these two surfaces, it will be a mess because of the, first of all, you have to use two different integrals, one for the surface of the paraboloid and the other one for the surface of the bottom part of this solid E, and then you need to find the corresponding normal vector fields, and you even want to evaluate your vector field on these two surfaces, which will be a very complicated integral.